heck? Hello? Yes? A threat to our entire universe? Someone's trying to harvest the power of a neutron star for themselves. I'm on the way. So in order to stop this guy, you first must know what a neutron star is and how they form. So let's go see one for ourselves. Alright, here we are to the closest neutron star. A good model to describe a neutron star is a spinning charged sphere. So let's draw one out real fast so then we can do some analysis on it. So here's our regular standard coordinate system. My pen doesn't work. And we draw this out. It's more like an ellipse, but whatever. So it's going to be spinning at some angular speed omega. And it's going to have a radius r. There's going to be an observation point out here in which we will observe it at distance r. And importantly, the distance from, well, the angle from the observation point to this axis is going to be denoted as psi. Okay, so the equation we're going to be using is the magnetic vector potential A of r is equal to mu naught over 4 pi integral kr prime over the separation vector r with prime to dA. Okay, so I'm going to label the vector potential as that instead of using it like that because that looks too much like an omega. And so yeah, to avoid confusion, I'm going to use that fancy, cursive, awesome looking r instead. So first off, what we need to notice is that the definition of velocity satisfies this, which means that we can get a matrix now, and we want its determinant with x, y, and z components of omega sine psi 0 and omega cosine psi. Now all this is from just looking at the diagram. And then so we have r sine of theta cosine. And so the book does the rest of this in detail. And so I will leave that up to you if you're interested in it because I'm trying to save time so we can get to the big ideas because that's what's more important. It becomes an integral of the form AR equals a bunch of constants out in front, and then you're going to have your integral from 0 to pi of cosine and sine over your separation vector, which will have a lot of things in it, and then your area element turns into what it does in spherical coordinates, leaving you with some stuff that goes out in front. So then once you do this integral, you develop a solution. There's actually two solutions for two kind of, geometries. So we're going to have mu naught r sigma over 3. And then this term right here is going to be omega cross r. And this can be represented for points inside the sphere. And we're also going to be left with mu naught r4 sigma 3r cubed omega cross r. Okay, and that, I bet you could have guessed it, is outside the sphere. So this is our general solution for our spinning sphere magnetic vector potential. So the important part now, I'm going to erase this board and do that. But before I do that, just take notice that this depends on omega. So we know that A is proportional to omega. That's going to be useful later. So for this next part of the derivation, we're going to start off with one of the Maxwell's equations. I'm sure you'll recognize it because we've used it quite a few times. So the first thing we're going to want to do is take note that the magnetic field is equal to the curl of the vector potential. That's going to be super important because we can rewrite this equation then as follows. Okay, so now what we're going to want to do is some fancy mathematical footwork, meaning that what we're going to want to do is multiply both sides by dot dA. So we're dot producting both sides with dA. So we're going to be left with this on this side equals negative d dt curl of A dot dA. Okay, now since we have differentials on both sides, our next line of defense is to integrate both sides. So remember that this is fine because integrals and differentiation are interchangeable in order. They do commute. So that's a very useful result. Otherwise, the next step wouldn't work at all. So what we're going to want to do now is use the curl theorem to turn this into the form of E dot dA equals negative d dt A dot dA. And now we can move this back inside the integral such that we're left with this. We're going to use some kind of strange notation. But now what we're going to want to do, and note that this next part is not always true, but in this case, it's fine to do just because of the certain quantities that we're working with. So what we're going to want to do is examine the inner arguments of these integrals. A way you could think about this would be that we're kind of unintegrating both sides, such that we'll be left with E dot dA equals negative dA dt dot dA. Okay, so what we're going to do here now is, remember that dot producting is just that times the magnitude of this times cosine theta. Well, our cosine thetas are just going to be 1, so both of them, so we don't need to worry about those. So we can kind of get rid of these dot products and be left with E is equal to negative dA dt, or in another form, we can write it as E equals negative A dot. Okay, that's going to be important now because we can start establishing proportionalities. Remember from our solution above that we had that A was proportional to omega. Well, what does that imply about A dot? That implies that A dot is proportional to omega dot. Okay, so then by transitivity, we know that negative E is proportional to omega dot. And now what does that tell us about angular momentum? Well, for the angular momentum, remember from classical mechanics that we have this definition for angular momentum. If we were to differentiate both sides, we would have that L dot is equal to I omega dot. Then we have omega dot is proportional to L dot, which is proportional to A dot, which is proportional to negative E. So we've established a chain of proportionalities which can help us to describe these neutron stars. So we do know that neutron stars have been observed to have a negative omega dot, which implies that their angular velocity is decreasing over time. Now, the reason for that is because they're obviously losing energy from, photon emissions and other forms of radiation, heat, other things like that. But what does that imply now about their E field? It implies that they have an E field that exists only because this is changing. So that's pretty profound. That's how the E field of a neutron star would be generated. Now, what the E field is definitely a question for another time. So now that we have this information, let's talk about how neutron stars were actually observed. Because they're very small, they are about the size of a bit larger than the size of a city on Earth, but they're quite small, like not comparable in the size of stars. So how do you observe them if you can't do that? Well, if you have a neutron star here, and just say the Earth is way over here. Okay, and this is one of the poles, one of the magnetic poles of the neutron star. Well, actually, at their poles, neutron stars emit electromagnetic radiation, which just blasts outward, and it reaches us. And also, due to their high, angular velocity, they rotate really fast, and this beam crosses over us many times. So, like, it can happen like every, 1, 2, 3, or 4 seconds that you'll get that blast from them. And so if you listen to them after you've collected data from like a telescope, you'll actually hear a pulsar. That's what they're called, a pulsar. You'll hear them and you'll know what it is because it'll sound like this. They'll be going like that because they're spinning really fast. And it's really cool that that's actually how we detect them because you can't like see them. It's quite fascinating. All right, I've made a portal to the perpetrator's ship. Now, where is he? Oh, I hear something over there. Whew. All right, there he is. Oh, who are you? Who am I? Who are you?